So, yes, I'll introduce myself. I'm Ian Sweat. I'm an IETF editor for the Quick Working Group. I also happen to work at Google, but here I'm going to really focus more on the IETF activity that I've been working on the last year or two. So in terms of the network, this is one data flow diagram from Wikipedia. We usually think about like network operators as focusing on the bottom half of this diagram. The links themselves and the lower layers of the network. But many of you are also looking at transport metrics and application metrics as well for a variety of reasons. And this presentation is really about how those things may change and have already started changing in the last few years and will continue to change, and how the IETF is shaping those. So I'm going to kind of go over what operators want, or at least I guess what they tell us that they want. I'm certainly not an expert, so if any of these things are wrong, these are sort of parroted things. But these are the concepts that we keep in mind at the IETF when we're developing transport protocols. They want to operate the network, allocate resources, resolve issues, assure availability. They want the performance to be excellent, right? They want the user experience to be good. No one wants their network down. No one wants their network with terrible tail latency, difficult to reproduce issues, all these things. And so that's kind of one of the cores of operating a network. You also want it to be secure. You want to identify actual security issues. You want to mitigate threats, look for viruses or malware potentially, prevent DDoS and other outage sort of issues. And impose policy. Imposing policy is a wide set of things, depending on the environment you're in. It could mean data loss prevention. It could mean filtering. It could mean auditing for legal reasons. But the technologies I'm going to talk about have the potential to impact how one does each of these things. So what's changing? First, I want to present to you kind of an image of how the internet mostly would look like 5 years ago. 5 years ago, I think we were, pretty much everything was HTTP, with a few exceptions, some bank sites, some login pages, all that stuff. So unencrypted traffic over TCP, many different connections for a single browser page load. That's sort of the model we were working on. So in the last few years, there's been quite a dramatic shift from HTTP to HTTPS, with the majority of the web now being encrypted. These metrics are a little bit old, from August 2017, so I'm sure it's even more now. But this has been a pretty rapid change. Certainly the Snowden leaks accelerated this, at least that's my perception of the process, but it was already undergoing prior to that time frame. And part of this has been the evolution and adoption of HTTP2. So HTTP2 was standardized in 2015. It's now in every major browser. It's about 45% of responses on the web. In practice, HTTP2 requires encryption in order to be deployable. Therefore it's encrypted. It adds multiplexing, header compression, server push, and connection coalescing. All these features, the goal of all these features really was to improve user experience, improve the consistency of user experience in terms of page load times, improve latency, and for most websites, it's managed to do that. So that was really the driving force behind this. But things like connection coalescing and the fact that you can now serve www.example.com and images.example.com from a single connection may start to change things. And the push towards encrypted traffic certainly changes things from a manageability perspective. So other things is, if you do intercept it, don't assume 1-1. That being said, in practice, it's always going to be encrypted, so you're not going to be able to intercept it. And so again, as I discussed before, it's not just one connection, one origin. There's connection pooling across different origins. So now we've already moved from a world where you have many, many connections for a given page load, and they're all unencrypted, and you can kind of see everything, to a world where you get an SNI for a single connection or 2 or 3 connections, and that's it. You don't see what's inside. You have no idea what the URLs that are being requested are, or whether they're even for the domains that were the same as the SNI. So it's a pretty dramatic change, and that's kind of in the last 5 years, I would say. Coming up in the near future is TLS 1.3. So TLS 1.3 is an evolution of TLS, the goals being faster connection and establishment and better security. The main impact from an operator perspective, potentially, and it depends on your environment, is it removes a variety of ciphers that are considered to be broken for a variety of reasons. And it moves only to ciphers which are perfect forward secure and use ephemeral keys. These tend to be more difficult to man the middle. And so if you're in an environment where you need to audit all traffic coming in and out of your environment, for example, TLS 1.3 tends to pose some problems. However, things like SNI are still in the clear. So if you're looking at standard web traffic going in and out and you don't need any auditing requirements or anything, it actually doesn't really change that much. One kind of note about TLS 1.3 and its evolution and deployment is this is a case where it's not just the IETF inventing a bunch of new crap that you have to deal with. This is a case where various people in this room may be affiliated with organizations that deployed software and hardware which actually made TLS 1.3 like a big pain to deploy. And so, our work kind of goes back and forth, and it's worth us keeping, both sides should keep the other, kind of informed of what their assumptions are and how we believe the network is evolving. In this particular case, there were a variety of issues where different pieces of software implementations had assumed that 1.2, the version negotiation and a few of the other features about 1.2 and how they worked were going to, continue going forward. And when 1.3 came along, everything broke. So, we managed to adapt around those things, but, I think it's a testament to the fact that the ITF and the members of NANOG potentially could benefit from closer interaction on a variety of issues in both directions. So origin and secondary certs. So I talked about connection pooling before. Origin makes that more powerful. So the origin frame simply allows you to say, you connected on example.com. By the way, I'm also happy to serve you, requests for all these other host names. So it kind of accelerates connection pooling. And secondary certificates are sort of, they're like adding a little bit of gasoline to that fire and saying, not only that, but that cert I gave you in the handshake, I'm going to give you like 3 more certs. So now I'm authoritative for like all of these things. So if you're a large CDN, this might be extremely compelling. So now I can have one connection to server user for a variety of different websites. I don't need any handshake latency. I can, reuse my SSL context. Like everything's wonderful. Like the user experience is awesome. It's very consistent. It's seamless. The impact on you may be non-trivial, right? You may be trying to tell like how many people are going to Google versus, some other website. And Google is probably not a good example because we don't actually coalesce with the, non-Google domains. But in Akamai or something, a large CDN might be an excellent example where they might host CNN and CNBC, for example. I have no idea who they host, but, and they might now be able to pull these things together. So there are a variety of innovative things that may be coming down the pipe there. So the next thing is Quick. Quick is currently deployed by Google. It's supported by all of our servers. It's in the standardization process at the IETF. It's been there for about 1.5 years. Almost every single byte on the wire so far has been changed. So, it's good to know that the IETF is doing their job well. But the core goals are very much the same. It's a UDP-based multi-stream transport. It tries to avoid TCP-style head-of-line blocking among the multiple streams. And it really tries to optimize as much as possible for the coalescing of like crypto, transport, and application layers. In particular, it really assumes that crypto is always available and you are always going to use it. And so there really is not the concept of an unencrypted version of Quick. It does allow mobility with the connection ID feature, so potentially you can switch from like Wi-Fi to cell and back and forth. You can also do multipath with a very similar mechanism, although that's not yet specified. And in general, I think the philosophy has been encrypt all the things. Crypto has gotten a lot cheaper in the last 10 years. And so now the assumption is like encrypting everything is great. It's relatively low cost on both hosts. And we pretty much already have to do it anyway because we're encrypting all of our traffic for HTTPS. So part of the Quick Working Group has seen a lot of influence from people who are very concerned about privacy. So this is just an article, screenshot from an article about someone who identified Netflix videos in real time using HTTPS fingerprinting. So they were mostly just looking at TCP headers. So, that's a transport layer signaturing. And this is just one of many approaches which are being shown to be valid in identifying what traffic is actually flowing on a network, even if it's unintentional kind of release of information. So things like this have definitely powered a fair amount of concern about from certain IETF members, particularly those in the security working group. And their input is fairly important to the evolution of Quick, partially because crypto is so tightly baked into it. So here is an overview of the current Quick wire format, which I am certain will change. I will absolutely guarantee you will change probably in the next month, based on the rate we're going. But the idea is that there's a bit at the very front that tells you if it's a long header or a short header. Long headers are used for the handshake. So the nice part about Quick is you actually probably will be able to very easily tell, hey, this is like a handshake, a SYN-SYNAC sort of equivalent, by only looking at the first byte of the packet. So that's a good thing from a manageability perspective. But almost everything else is mostly trash, is what it comes down to. There's an approach called greasing, which means you use a variety of code points that you're not currently using, or you act like you use them, just to make sure that the network doesn't ossify around those code points not working. We're likely to use that in various parts of the header if there are any bits that we're not currently using in version 1. There's an opaque routing identifier, which does not change very often, but it's intended for use by routers at the endpoints, so essentially load balancers, not really for network operators. There's a packet number, which is currently sequential, which is somewhat analogous to a TCP segment number, but it's likely to be encrypted, so don't worry about that. And then the rest of it's encrypted. So it's pretty much garbage. So there's not a whole lot here you can really look at to get transport level information. You can definitely still look at the handshake. We're still going to be running TLS over this, so you're going to get SNI. But after that, it's just going to be mostly UDP packets on the wire. So talk about connection IDs a little bit. Quick connections are identified by connection IDs, at least in some sense. They're not identified by a 5-tuple, at least that's the concept. That being said, 5-tuples are likely to be relatively stable in deployments. There are some very practical reasons why, for most cases, most connections are only going to be over a single 5-tuple. It's just how the network works today. The network is set up to run that way, and we will continue probably to deploy it that way. And that's certainly how Google's deployment of Quick has been working. But that being said, the idea is that connections may migrate across 5-tuples. And there's also the ability to change the connection ID during the handshake in order for a load balancer to direct traffic in a different way. Operator impact. So obviously it's a new transport protocol, new tools. Traditionally we've had some level of Wireshark support already for Quick. I think that will actually improve quite a bit, especially once it gets closer to IDF standardization. But there's still a shift there. There's the shift to UDP. There are certainly some people who have made assumptions that all UDP traffic that is not DNS is kind of low value. Certainly, Google doesn't think that way at the moment, given that we're sending search queries to google.com over that and playbacks to youtube.com over that. So that's not our perspective, but I do understand the reasons why there's a long-held dislike of UDP, particularly port 80, which thank goodness we're not using. The encrypted metadata means that you can't see RTTs as easily. You can't induce or kind of infer the loss rate of the connection as easily as you can in TCP. So those transport level metrics, at least at the moment, are not present. Now, there is a conversation at the IETF about kind of reintroducing those into the Quick packet. So, having some number of bits for manageability. And it actually turns out that with only 3 bits or 2 bits in the first byte, you could get a fairly good signal of loss rate and RTT. So, this is not technically infeasible. But there are still people who basically are saying, the more bits you expose, the the worse it's going to be. So it's certainly an interesting discussion, and I don't think the IETF is close to consensus at the moment. And there are some IETF folks who are going to be talking later who can ask, or answer more questions about that. Also, the network can't just reset connections, at least post-handshake. So once the handshake is completed, TCP, TCP, obviously, you can just reset it quick. There is something that a mechanism where you can reset a connection, but you have to be part of sort of the server farm that originally set up the connection. So it's kind of an encrypted reset of sorts. As I said before, connections are no longer identified solely by 5-tuple. Also, I will say that there's a lot of discussion around what connection ID is going to look like. It's possible that there will be bidirectional connection IDs, so one going in each direction. It's almost certain that connection ID will be optional. So again, it's kind of up in the air, but the moral of the story is that probably, assuming 5-tuple stability is a better idea than assuming connection ID stability. DOE. So DOE is DNS over HTTPS. This is a relatively recently created working group. September 2017. DOE is a pretty simple concept. So, the goal is to actually finish this off quite quickly, is my understanding, maybe even in 2018 for the most part. So, you've seen probably overall a variety of things head towards the let's put everything over HTTP or HTTPS, approach lately. And it's mostly because the tools are amazing and everyone knows how to deploy it and all of those things. And DNS is yet another case of, let's put this over HTTPS. So there is already some ad hoc deployment. Google DNS supports kind of a beta or early version of it just for testing. I know there are a few other people who are working on early deployments. And I think the motivation comes from a few different angles. So there's the privacy aspect we talked about before, and DNS certainly does leak a fair amount of privacy information. It tells people like which websites you are visiting. So if, illegal.example.com existed and you connected to illegal.example.com, everyone in the world would know that you connected to illegal.example.com, in the status quo. And, DNS over HTTPS would solve that problem. On the other hand, it also poses huge challenges for people who are trying to, prevent people from going to illegal.example.com, especially from places like schools and such. It's also worth noting that performance is a major compelling use case. So DNS over HTTPS, well, that sounds really heavyweight, so obviously that's extremely slow. But if you look at the latency profiles of DNS versus, say, HTTP first response byte, what you'll see is that up until the 90th or 95th percentile, DNS is definitely faster. But after that, the fact that you have much better loss recovery in TCP even is a huge boon. And then when you have QUIC and you have no head of line blocking, you may be even in a better place. So I think there are actually some potential performance benefits here too. You also potentially could use HTTP2 server push. So one of the motivational items that came out recently was there was a nice IETF presentation at IETF 99 about the rate of Google DNS, and I believe this also applies approximately to, is it OpenDNS? That over 1% of DNS traffic was being hijacked. So you thought you were using 8.8.8.8, but in reality, someone else was replacing it with something else. And this was fairly widespread among a variety of areas in the world. It did vary by region quite substantially, but people found this fairly concerning, and this certainly was motivational work for creating the DOE working group. So this is possibly a bit overly dismal of what the operator impact is, but I think it's best to have worst case scenario. Split DNS, which many people would argue is a questionable idea anyway, but it certainly has the ability to break that. And all of this depends on which DOE server you are connecting to. If you were operating a DNS over HTTPS server locally, and that was the exact same server that was being contacted before, then ostensibly nothing was changed because you could still block someone from visiting illegal.example.com and so on and so forth. But yeah, in general, policy enforcement and data gathering, unless you're controlling the DNS server in question, are going to break. Certainly the ability to passively look at what DNS host names are being visited, goes away. So I think of all the things I've discussed, it's possible this has some of the largest operator impact for different types of operators. And it's also the farthest from being deployed, so I think it's difficult to project how it's going to develop. No one has really deployed this at scale. There's the example at Google, but no clients are default using it, So as a summary, the internet enables kind of permissionless innovation by design, and that's kind of one of the greatest things about the internet. I mean, it really has evolved by allowing people to do cool, new, amazing things, and not having the U.S. government or someone else in the way of that process. But a lot of things have changed even relatively recently. And some of these things, particularly on the transport and application side, could really affect how people operate their network, even if that wasn't the intended reason for the change. So there's a huge amount of focus on stronger encryption, partially because of reduced cost, also because of increased concern. There's kind of a push towards applying policy and management towards the edge. So changes to things like BBR congestion control are another example of a move towards end-to-end congestion control opposed to point-to-point. But I'm here to kind of present these ideas to you and encourage you to get involved and interact with the IETF and understand, and maybe interact with your vendors, a priori, and understand how different people can help you adapt to these changes, and potentially how the IETF can make them less painful, assuming that's possible. So, well, thanks. First question.
Sure. Hi, I'm Kevin Locke with QTS Data Centers. I have a couple of security/privacy concerns. First of all, thank you very much for giving this. I'd love to see more IETF/NANOG interaction. I think that would be great for both groups. The first is the connection pooling and gratuitously pushing SSL certs seems to be a real I'm hoping this has been addressed already and it just was skimmed over. It seems to be a real security problem because you're bypassing the sort of the two-factor authentication that DNS and especially DNSSEC could provide.
Yes.
So, and as we know, SSL certs can easily be obtained, either through incompetence or if you're a nation state or even in a corp IT department, there could be a lot of problems with that.
Yeah. So there are a huge number of restrictions on what you can add as a secondary cert at this point. I can't remember I follow the security working group, but I'm not as active of a member. But I believe I'd have to look up what the restrictions are, but there are a variety of restrictions that kind of enforce, like you have to either do a revocation check, I believe, before using it, or check some other like log-based source.
It would be great if you would force a DNS, especially if DNSSEC is available. That would seem to be a really good secondary check. The second issue is, with all this modernization of HTTP traffic, has any thought, and with respect to privacy, has any thought been given to reducing the granularity, resolution, and detail of browser version numbers that are supplied, which can obviously be used to fingerprint users and correlate between widely different sites that you might use? That's
a good question. That hasn't come up at the IETF because I think that's a kind of an implementation specific issue, but you make a good point. I think that's...
Yeah, I think it's a lot bigger problem. Some articles have been written on it. I think it's a much bigger problem than most folks realize, is how easy it is to fingerprint down to 1 in a billion users, just because, especially with all the different plugins and fonts and everything that users have that makes them unique. So.
Yeah, good points. Thanks.
Toma Gavrichenkov speaking, Curator Labs. First of all, thank you for your presentation. I have a couple of questions. First of them is a recent study from Asia Pacific Network Information Center Labs shows that QUIC performs significantly worse than TCP in case network reorders packets. I wanted to ask you if the working group is aware of it. Is there going to be some solutions for that? Don't you know?
So I actually don't think I've seen that study. So if you wouldn't mind, could you send it to me afterwards?
Yeah, of course.
Oh, thanks. So I have seen some similar data that we have internally, and that's a implementation artifact and not a standardization product is the short answer.
Okay.
The reason is Google Quick was lazy, and we didn't bother to implement adaptive reordering tolerance in terms of packet number distance, and the kernel, Linux kernel, does implement adaptive reordering. So as reordering increases beyond 3 packets, the default that we use and the kernel uses, Quick starts to suffer fairly severely. So it's on our list to fix that as an implementation artifact, but it's the spec currently allows you to implement adaptive reordering and kind of says that that's a good idea. It's just our code doesn't.
Thank you. And the other question is related to implementation of Quick. Don't you know if Google is planning to do it in like for Linux in kernel space or user space? Because this is actually what may affect operators. Because if Quick server runs in user space, then you're essentially pushing what was before TCP handshake from kernel space towards user space, which allows for all sorts of denial of service attacks and stuff.
Right. So currently all the Quick code that Google has is user space code.
This is actually what can affect a network operator in my mind, because they will need to replace like their security solutions with others. Okay, yeah. Let's see it. Thank you very much.
Welcome.
Hi, Dwayne Muscles from VeriSign. You mentioned almost in passing that when Quick is used for HTTP, that TLS is also used. So it's doubly encrypted?
Currently, it's a little bit complicated. So the status quo of what Google Quick has its own Quick.
Maybe not so much what Google Quick has, but what's the IETF? What direction are they heading in?
Yes, it will be TLS. So and it won't be double encrypted. It will be using the TLS handshake, and then it essentially does key export, and then encrypts the entire payload of the packet.
So it is doubly encrypted, or
it's singly encrypted.
It's singly encrypted. Okay.
It's singly encrypted, but the way we're running TLS over stream 0 and then doing key export for the rest of the payload.
Okay, thank you.
You're welcome.
So Warren Kamari, Google, and also the tech advisor to the DOE working group.
Oh.
Hey, so kind of responding to Kevin's earlier question, with the DOE stuff, you can probably still do all of the DNSSEC stuff as well. You know, you can still get all of the information. But possibly more relevant, there's now a TLS extension which will actually carry all of the DNSSEC stuff included in it as a chain. So that way you can still do, you know, normal SSL validation and the DNSSEC/DANE stuff as well if you want.
Thank you very much.
Avi from NANOG. What are the plans for congestion control management for the Quick?
So Quick currently standardizes the one congestion controller that is at all modern, that the IETF has standardized, because that's what it is limited to do in its charter, and that is Reno. So the congestion control and loss recovery document specifies Reno, new Reno, as the congestion controller. And essentially for loss recovery, it will specify like a variant of RAC, if you're familiar with the recent RAC work. We would be happy to specify another congestion controller, but yeah, none of them are standardized at the IETF.
Okay, so it's part of the header, the congestion control.
It's the congestion control feedback is part of the transport, but the which congestion controller is run as a specification, there's a recommendation to do Reno, if that makes sense.
Okay, thank you.
I'm Spencer Dawkins. I'm the Transport Area Director, so I'm the responsible area director for Quick. The point about the congestion management mechanisms that are in use is that I started working on transport stuff at the IETF in like 1996, and Reno was a thing, and Reno is still a thing. And that had to do with two things. One was everything being implemented in kernel space, so that you had to wait to, your users were going to have to upgrade their operating systems in order to change that. And then all the middle boxes that kind of knew what Reno was and were trying to dork with it anyway. So between those two things, that's why the state of IETF protocol congestion standardization is what it is. We've had other ideas. The question was, how do we deploy them? And what you're looking at is a group of people, not me, the working group, people like Ian, who are working on transport protocols that can run in user space that can be upgraded without having to roll operating systems. So that makes it a lot more interesting for the IETF to look at some of the ideas that we've had, and even ones that are being done in the Internet Congestion Control Research Group at the IRTF, and say, what of those are, what's baked, what's ready, what was a good idea, except we didn't know how to deploy it. So things are going to be more exciting in transport in the next 10 years than they have been in the last 10 years.
Thank you.
More at 5 p.m., of course.
All right. If there are no more questions, then thank you very much for having me.
Thanks. Thanks, Ian.